video, we'll be discussing the question of pointwise convergence, which is actually an important topic from CSIR point of view. So the question says that we have a sequence of real valued functions which are bounded. Fn is a sequence of bounded real valued functions on R such that Fn converges to F pointwise on R. So will F be bounded? The main question is, will F be bounded in this case? So you take your time, pause the video, and think of the answer whether it is yes or no. If you have a yes, if your answer is yes, think of a proof. And if your answer is no, you should be having a counter example for it. So the answer to this question is a big no. No. That means we have some examples for which we can construct Fn's to be bounded, real valued functions on R, converging to F pointwise, but the limit or F is not going to be bounded. The pointwise limit is not going to be bounded. So my example is Fn. Define Fn for each n greater than equals to 1. Define it as 0 when x is less than equals to 0, when x is greater than equals to 0, or less than equals to n, then it is n. And since I am defining it to be continuous, I can put equal on both sides. And for x to be greater than n, let it be like this. You have it. Sorry, here it is x, and for x greater than n, this constant n only. This is n and this is x. So here it is the identity function. And after n, it is taking a constant value n only. So it is a continuous function because if you check before 0, it is 0. Till n, it is taking the value n. It is just the identity function. So till n, it will be taking n. And after n, it is taking constant value n. So you can see that it is a continuous function because there is no break. There is no break at all. And what about boundedness? Is each Fn bounded? So each Fn is actually bounded because if you check the value here on the negative real axis, then it is 0. In between 0 and n, it is identity function x. So the maximum value it will be attaining on the bounded interval will be this only n. And after that also, after n also, it is n. So the maximum value is n. For each Fn, it is n. The maximum value is n. Since it is a non-negative function, it is not taking any value in the negative, taking any negative value, and on the negative axis it is 0. In between 0 and n, it is identity function x, and after n, it is n. So it is a continuous function as well as a bounded function. So each Fn is continuous and each Fn is bounded. Although continuous is not required in the question, but my example takes to be continuous. So to satisfy the hypothesis, we need Fn to be bounded, real value. So you can see that Fn is from R to R only, each Fn, and should converge to F pointwise. So will this sequence converge to any function? So if you check this for some values of n, we check this for some values of n, then for F1 till 1, So if you try drawing the function for f for n equals to 1, so f1, so that means 0 on the negative axis till 0, it will be taking the value 0, and between 0 and 1, since n equals to 1 in this case, so between 0 and 1 it will be the identity function, and after that it will be just constant. It will be constant like this. If you talk about f2, then as usual on the negative real axis it will be 0, since n equals to 2. Between 0 and 2 it will be the identity function, and after 2 it will be the constant function, or constant, it will be taking a constant value 2. Similarly, for n equals to 6, for n equals to 6, it will be till 6, it will be taking the identity function value is 6 till here. It is like this, and after 6 it will be constant. It will be taking the constant value 6. So this is how the sequence behaves. Now if you see closely, then the sequence converges to a function f. Sorry, converges pointwise, so there will be a single arrow. And what is the function? See, on the negative real axis, each f1 is 0. At each point, f1 is 0 here. So that means the limit function is going to be 0 for x less than equal to 0. But if you see for here, it is identity function on a bounded domain. So our limit function is going to be x when x is greater than 0. Why x? Because, see, if you choose, if x is in R such that x is less than equals to 0, then fn x equals to 0. Let us make it x0 so that you know that it is some x0 is fixed. Okay, x0 is fixed. So for that x0, which is less than equals to 0, fn x0 is 0 for all n. For each n, fn x0 is 0. If x0 is greater than 0, then by Archimedean property, there exists an n x0 in M such that x is less than n x0. You take any positive real number, of course you can get a natural number such that that natural number is greater than your chosen positive real number. For example, if you take 3.5, then take 6. 6.5, 6.6, you can take 7, 8, anything. But you just need one natural number. You will be getting a natural number such that that number is greater than your chosen positive real value. So this is possible. This is always possible. And now if you look at the graph closely, for each n, till some natural number, it will be an identity function. It will be the identity function, and after that, it will be a constant value. So usually their aim in pointwise convergence is for every epsilon and for every x, or for each epsilon, for each epsilon greater than 0, and for each x, there exists n such that it depends on both your x and epsilon in the case of pointwise convergence, such that fn x minus fx is for selected. And it is for selected. So it is better if I write it this way. So for epsilon greater than 0 and for x in R, there should exist a natural number in n such that this is true. For all n greater than equals to that n x epsilon. So it is not, we are in pointwise convergence, we don't want to this to be fulfilled for every x, but for a particular x and for a particular epsilon, we should get an n such that this is happening. But in this case, we can't just reduce the difference, or we can't just make the difference less than epsilon. Actually, we can make it 0. For any x, we can do that. Because if you see, I told you that our function, the limit function is x. That means the function is going to be like this. It is going to be like this. It is going to go forward forever and ever because it is in R and the x-axis extends to infinity and the function is identity on the positive real axis, so it will extend to infinity. And for any x, for example, if you choose 5, then you know that f4 is x when the x is 0 to 4. You know this is happening. But when it is greater than 4, then it is 4 only. That means on 5, at 5, this f4 will be like this. It will be taking 4 value only. But if you think of f5, then you know that f5 behaves as identity function till 5, and after that it takes the constant value 5. So that means you are able to get an n such that the limit function and the fn actually overlap till some value. They coincide. And this is the reason I was saying that for every x you get a natural number so that this is happening. So that x is less than nx naught. This means x belongs to 0 to nx naught. This means that f nx naught at x will be identity because x in this interval and f nx naught is identity before this nx naught. And what is fx? It is also x. So fn x naught, x minus f, x is 0. And of course, you can make it smaller than any epsilon greater than 0. But your condition says that you need an n such that fn x minus fx is less than epsilon for all n greater than equals to n. So if you take n such that it is greater than equals to this nx naught, then if x belongs to this, then of course it will be in this also. And for that case also, fn x is going to be identity function only. So fn x minus fx is actually 0, which is less than any epsilon greater than 0. So in this case, we are not able to just reduce the difference, make the difference smaller than epsilon. We are actually able to make it 0 because our function, our fn's are actually overlapping with the limit function to some extent, in some bounded interval. f1 overlaps till 0 to 1, f2 till 0 to 2. But actually, we are able to obtain this nx naught using Archimedean property such that the difference is getting smaller for nx naught. And after nx naught also, if you take any natural number, n that is greater than nx naught, then if x was lying in that, and this x was particularly chosen. This x was, actually this was x naught to show that it was not arbitrary or random. It was arbitrary and random, but it was fixed, something fixed. So this was x naught. This was x naught. This was 0, and for any n that is greater than nx naught, you can see that if x naught is lying in this, then x naught will also be lying in this. And for that, the difference is actually 0. So the convergence is pointwise, because for any x you can obtain a stage after which the difference between fn's and f is less than epsilon, and in fact it is actually 0. So okay, so that convergence is happening pointwise for sure, but is f bounded? You can see that f is not bounded because f will extend up to infinity. F is not bounded. For 100, it will be taking the value 100. Identity function is never bounded on an unbounded interval. See, the interval 0 to infinity is unbounded, and on that interval, f is acting as the identity function. So it is unbounded function. So the answer was no, and this was the example. If you have any other example, let me know in the comment section. Till then, happy learning, and thank you so much for watching this video.